All right, let's start today's class. So, this would be the week 12th class, but I mentioned that last time this would be our last class. Turns out that we will have one more class where I will be revising all the, you know, all the week's content, in the next class. Okay, next class is going to be on same time, Saturday 7 to 9. Uh, so feel free to attend, and if you have any questions, you can come and ask in that session. In addition to it, this week what I will do is I will just go through one problem regarding droplet combustion, and this is going to be useful for your assignment. Um, and one more thing I want to discuss is your exams are going to be happening after our next class. So I I encourage you to prepare for that. And if you face any difficulties, please come back next class and you can clear your doubts. So having said that, let's start our discussions on droplet conversion today. So what do we have here is usually droplet conversions are important in a lot of places, uh, especially in rocket engines. Um, Even sometimes in gas turbine engines, the fuels are always in liquid state, and we try to we use a atomizer, or you can call it nozzle. We will try to break that liquid you know into small droplets. We will try to spray it so that it becomes small droplets, and those droplets reacts with gases and it starts burning, and the fuel gets consumed and products are formed. So that is the droplet combustion phenomena that we see in lot of places, including rocket engines, from rocket engines, gas turbines, even in CI engines, right? In CI engines, we spray the diesel, right, inside the combustion chamber, and what happens is the liquid droplets sometimes may evaporate because of its size, very small size. Uh, it might evaporate, and then the gaseous fuel and gaseous oxidizer reacts and it forms the products. Either that could happen, or sometimes it might stay as a liquid droplet. And what happens, the, as soon as it starts evaporating, it reacts with the oxidizers, and then it forms the flame, then it produces products. So that's what we see here. So basically I took this you know a image from one of the research paper. So it's a interesting image. So basically this will be our droplet, and will be fully liquid. And what happens, liquid becomes vapor. I mean, it gets evaporated here, and then you see a flame around it. Okay, so the vapor comes here and the oxidizer meets here, and both of them combust over here and products go everywhere. So that is the concept. That is how the droplet combustion happens. And basically there will be nozzle or atomizer, spray atomizer, which generates fuel droplets. In even in rocket engines, what happens, there will be two nozzles similar to this. One will be for fuel and one will be for oxidizer. And what they do is they try to spray both of them inside, and these two, fuel droplet and oxidizer droplet, they interacted with each other and the combustion happens, and high temperature, high pressure gases are generated inside the combustion chamber. So that that is also in a way related to droplet combustion. So in fact that is even complicated than the droplet combustion, but basically it derives the the physics from the droplet combustion. So let me just draw you. So, but you might be wondering, how does droplet evaporate? So because it needs some uh, energy for it to evaporate, right? So let's say this is the fuel droplet. Now let's say oxidizer is present everywhere. So now what happens when the fuel evaporates? So the fuel, let's say somehow it evaporated, okay, for now. So once it evaporates, it's a gaseous fuel, and you have oxidizer everywhere. So outside we have oxidizer. So now let me call oxidizer something like this. Okay. So now what you will see is, so this oxidizer is present everywhere actually. Uh, Now the fuel here and the oxidizer will meet at some point, and it starts combusting. So it requires fuel and oxidizer, right? And also the temperature would be a little higher. So those things are required. So uh, when it started combusting, we see a flame over there, and this is going to happen throughout. Okay, I mean, this is going to happen, surrounding the fuel droplet. Now what happens? Since combustion happens, there is a temperature is very high here, and at the fuel surface the temperature is going to be T saturated, because fuel is just what it does is phase change is happening. So phase change happens at saturation temperature. So this will be at, let's say, T sat. And now what we see is we have temperature, very high temperature over here. Let's say we call it T adiabatic. Okay, and let's say this is some temperature T infinity, and what you see here is, if I try to draw it as an, let's say, R axis. So how the temperature profile looks. Okay, so let's say this is R axis and this is temperature, and this coincides with the T. So this is the surface. Okay, R equal to 0, or this is at the surface of the fuel droplet. Now if you look at here, it is going to be a T sat. Temperature is at T sat, and after. Okay, so after some distance where the flame is, this is where the flame is, and at this point the temperature would be a little high. It will be T adiabatic, right? So what exactly happens is, you will have a temperature gradient from the flame surface to the uh, fuel surface, and this actually gives rise to conduction, and because of conduction there is heat is going to come to the fuel surface, and that heat is going to be used for evaporating the fuel. Same like we uh, it's same like when we studied the premix flame, right? We have to preheat the, fuel from low temperature to a ignition temperature, right? If you remember correctly. So uh, the same preheating here, it is in terms of the same energy is used for phase change. That's it. That is that is due to the fuel is in the liquid phase and reactions are happening at gas phase. There are other types of combustion also. There are solid combustion, where the particles will be there and the particles will be solid, and on top of that the gases comes, and on the surface it reacts. So those are surface chemistry, those are little advanced topics. That's why we stop right here. So in droplet combustion, what happens is there is a phase change happens and the gas phase like chemical reactions happen. So this is the concept. I was just refreshing you the concept, how it actually happens. So we will keep this in mind for solving today's question. Okay, so let's keep this aside. So we are going to do some analysis of this droplet. Let's say we have a single droplet. What is the time it takes? What is the total time it takes for it to evaporate fully and combust? So that is called droplet lifetime. And what is the burning rate of these droplets? And if this is the burning rate, what is the you know temperature at the flame temperature basically? What is the flame temperature? um, and uh, and we are also going to see how distant this flame is from the surface. That will also we will see. Sometimes what happen, the flame would be very far away from the surface. Sometimes it might be very close to the surface. All those things can happen. So let's say if it is very far, what happens? Let's say if you have a lot of droplets, though one or two droplets can like agglomerate together, and it might create a complex dynamics inside. So those are few things which we need to take care. So that's why it's also better to know where the flame stays from the surface of the droplet. All those things are useful for for preliminary analysis. In ideal, these are all for ideal situations. In real, these kind of analysis will not be helpful for accurate predictions. In real life, let's say if you want to you know find out how much time does a inside a rocket engine, let's say how much time does the droplets generated, let's say at 100 micron droplet, or 50 micron droplet, how much time does it take to fully burn, right? Because that is going to influence your um, design of the combustor. So that is going to influence how large your combustor should be, because all the droplets has to be evaporated and it has to combust within the combustor. If it doesn't do that, it can easily go. It will just go out of the nozzle, and we will lose all the energy. So basically, what the combustor does, it just converts the chemical energy, which it has stored, um, which is stored in the chemical bonds, right? In a fuel, uh, the energy is stored in terms of chemical bonds, and during reactions, these bonds are broken, and it reacts, and it forms a different species, right? So this chemical energy, you are converting it into thermal energy. So you want very high temperature as possible. So if you are not doing it, let's say in a rocket engine, if you are not, if your combustor is very small, and you directly attach a nozzle after that, then it becomes a problem, because the just fuel droplets will be going outside instead of hot gases, right? And that will create a very that will affect your efficiencies very badly. So that is the reason we need to find out this droplet lifetime, right? Lifetime of the droplet. That could be essential to design this combustor, but this is a crude estimate. It might tell you that this should be my length of combustor, but in reality, because of turbulent flows, because of multiple droplets present inside, you may not be able to. I mean, the combustion may be faster or may be slower, right? Maybe even order of magnitudes faster or slower. So all those analysis requires detailed research, and also detailed modeling, like for example, let's say CFD modeling. So such kind of modeling will give you better insights than doing such preliminary exercise. But preliminary exercise will give you, physical insights. What are the different parameters which is going to depend on, my droplet lifetime. Let's say if I have higher, HFG. So for phase change, we need some energy, right? So let's say if I have higher energy, if I require higher energy for phase change, will my droplet lifetime increases or decreases? Those are the questions you can qualitatively answer by this kind of analysis, and that's why it is very essential. It will also give you a physical insights of the problem. What are all the parameters is going to depend on your design, and how it is going to affect, right? So those are the important physical insights you can get. Um, but to you should resort to detailed modeling when you are doing a very detailed combustion analysis. All right. So with that introduction, let me just go through the first question we have here. In fact, I have only one question today, um, because I felt this was the one question you might feel little, you know, you might feel it is little difficult to solve. So I thought I will explain it to you better. And the other questions should be straightforward for you to solve. All right. So this question I actually took from the Stephen Turns, and the question is: there is a rogue fuel droplet escapes from a primary zone of gas turbine combustor. If both droplet and combustion gases are traveling at 15 meters per second through the combustor, estimate the combustor length required to burn out the rogue droplet. So basically, what happened was, in a gas turbine combustor, there is a primary combustion zone and there is a secondary combustion zone. In primary combustion zone, what do we expect is, where whatever the fuel we spray into the combustor, it has to evaporate, and either it can react. I mean, most of the reactions should happen, or at least gaseous fuel oxidizer product mixture should be exiting the primary combustor. But what happened was, there is one fuel droplet escaped. So that's what they call it, rogue fuel droplet. So basically, the one fuel droplet which didn't evaporate, uh, maybe because of its large size, probably, escaped from the primary zone of the gas turbine. So let's say if it was a bigger, so it escaped the primary zone of the gas turbine. Now, if both the droplet and combustion gases, if both of these droplet and the combustion gases surrounding it is moving, so it's a transient phenomena, right? The gas turbine combustor is at, let's say it's an aircraft engine, right? In a aircraft is keep on moving, right? So gases are keep on entering and leaving. So when the fuel is sprayed for the first time, during the operation, the one big droplet came and it couldn't fully, evaporate from the primary zone of the combustor. Then it entered the secondary zone of the combustor. Now, what they are asking us to do is, if this droplet and the gases surrounding it enters the combustor at 50 meters per second, then, I mean, the secondary zone of the combustor, estimate the combustor length required to burn out this rogue droplet. We want all the droplets to be burned, right? Let's say in a gas turbine, if you don't do that, what happens? The droplet, let's say if it doesn't fully, you know, combust, right? Then it will be a hot, liquid droplet. And now if it directly, the next, machinery after the combustor is turbine, right? We have a turbine after combustor. So now if this droplet goes and hits the turbine, it's going to be really bad for turbine. The reason is, turbine will have some higher temperature limit. It cannot have very high temperature. So let's say this droplet is burning, and its flame temperature is typically it's 2000 kelvins, right? 2000, 2200 kelvins. Imagine there is a 2200 Kelvin liquid droplet, uh, not just liquid droplet, but droplet with flame whose temperature is 2200 Kelvin. If it just goes and hits the turbine, right? There are no materials till now for turbines which can withstand 2000 kelvins, 2000 or 2200 kelvins. Even if there are, we may not know, because it's very highly secretive information. No one likes to share it, even, you know, all the uh, it's like a state of art technology. Whoever has it, they are the uh, money making companies. Okay, basically the Pratt and Whitney, GE. So all of these people, they know what the material they are using, but they don't release it. So uh, probably, as far as my knowledge, what I speculate is maximum temperature it could reach is 1800 Kelvin, or yeah, maximum 1800 Kelvin. So if the 2000 2200 Kelvin, if it goes and hits the turbine, it's going to be really problem. It might melt the turbine blades, and that might cause a problem. So you want all the droplet to burn inside, and also it also affects the emission. So you will be leaving hydrocarbons outside the combustor to the environment. So all these issues are there. In addition, you will also lose the performance. So some amount of mass with that much heating value, chemical energy is just going out of the combustor. That much amount of energy you lost, right? So efficiency lost is there. Materials, uh, you know. There is a limit on temperature. There is also emissions problem. So all these directs to some directs to only one aim, which is to evaporate this droplet and combust it fully within the combustor, right? That is our aim. And if we want to do that, then what should be the length of the combustor we need to use? So that is what we are trying to find out here. So there are few given there are few quantities which are given in the question. To simplify property evaluation, assume combustion product have same property as air. Okay, so the gases uh, which is coming with the this bigger rogue droplet have the same property as air. For the fuel droplet, use n-hexane properties. So the fuel is nothing but n-hexane. Assume the liquid density is 664 kg per meter cube. This is the droplet liquid density. Assume Ts. Ts is surface. T boiling is boiling temperature of the droplet. Using the Clausius-Clapeyron equation for boiling temperature at a given pressure. So they were asking us to find the boiling temperature based on the Clausius-Clapeyron equation. And other pertinent data are pressure. Actually, the pressure should be 10 atmosphere. So let me quickly change it. All right. So okay. So the pressure is 10 atmosphere, and temperature of the gases is T infinity. So I just wrote it like this: T INF is 1400 Kelvin, and the droplet diameter we have is 200 microns. Okay. And now what we are supposed to find? As I said, we need to find the combustor length. In addition, you can also find all this: the mass burning rate, the length of the combustor, so same as here. Find the flame temperature, find the ratio of flame radius to the droplet radius. Okay, so let's solve this. Let me just write down some given data. So the fuel is N-hexane. Alright, fuel is N-hexane, and the rho L is nothing but 664 kg per meter cube. Alright, and pressure is 10 atmosphere. T infinity is 1400 Kelvin, and the droplet diameter is also given, so 200 micrometer. And another thing, the gas and the droplet and the gases both move at 50 meters per second. All right, let me quickly draw what I'm trying to say here. Let's say we have this is our combustor, let's say, and we have nozzle over here. So this is where fuel enters, and this is where gases enter. So what happened was there were small droplets here. So maybe I will draw this thing. And there was this big droplet, which is the rogue droplet. Okay, and say this is the primary combustion zone ins. While it goes to the secondary combustion zone, we still have this big droplet. Okay, but now it is going to have flame also with it. We are going to analyze that. Okay, all right. Uh, okay, so I hope the question is now clear. Now we need to find the mass burning rate of the droplet. So let's just find mass burning rate of the droplet. Okay. So how do we find mass burning rate of the droplet? Droplet. So basically uh, we didn't really derive it, but we understood how it has to be derived, right? So in the classes, in the notes. So you can take a look at the notes. So I have the equation here. So and there are few assumptions in order to you know apply this equation. Please make sure you know that. Okay, so the mass burning rate of the droplet is 4 pi kg rs divided by cpg into ln of 1 plus b. All right, so we have lot of things to evaluate here. First thing is we have this b factor, right? So how do we get b? For that also we have a relation. B is nothing but this is for burning droplet. We are interested in combustion. It's not just evaporation, or it's not just mass evaporation due to mass transfer or heat transfer. Plus CPG times T infinity minus Ts whole divided by QIL. This is um, interface to liquid. Okay, the heat transfer from interface to liquid, plus HFG is nothing but the energy required to phase change. Alright, this QIL, let's write QIL also. QIL is nothing but Cp of liquid phase into Ts minus T naught. Now we don't know whether the liquid has any initial temperature or not. It is not given also. Let's assume that surface temperature is same as liquid temperature, or let's say you can even say that the whole entire liquid is in saturated temperature. Okay, so basically what I'm saying is Ts is equal to Tsat, which is also Tsat is nothing but T boiling. So that is also they gave, right? T is equal to T boiling. So basically that's what we are putting it here. So let's say if we do that, assuming Ts equal to T naught, then this QIL is equal to 0, right? So there is so whatever the heat comes to the fuel surface is used only for evaporation. It is not heating or it is not cooling the droplet. That is what it means. The reason is the droplet is already in saturated state. Okay, all right then. So we have QIL is 0, and we have we need HFG we need to find out. We need to find out delta HC. We need to find out nu. Nu is nothing but uh, mass of the oxidizer by mass of the fuel. That is what nu is. Um, CPG is this is where a lot of things comes into picture. The reason is when they derived it, they just wrote CPG. While they're deriving it, they also made few assumptions based on telling that Cp is constant for gas, Cp is constant for fuel, and you might end up getting. Uh, I mean, you can use a. Just give me a second. All right. So what I'm telling is QIL is equal to 0. The reason is droplet is at saturated temperature, and we were talking about CPG. So the CPG is so the CPG could be um, it could be either the gas phase CP, or it could either be fuel side CP, right? So while deriving, we made certain assumptions for getting this CPG. Um, so basically, if you get a good estimate of CP, let's say assuming all the gaseous mixture, then your answer would be more accurate. That is one thing. And delta HC we know it's a heating value, and all others should be straightforward. So uh, let's first try to find out HFG. Um, okay, how do we find out HFG? So HFG actually we can take it from the tables. It's for n hexane, right? So I from tables. So basically, I'm using Stephen turns. I think the table number is B3. Let me check that one. Right. So we have table B3 in Stephen terms. Okay, table B3 has CP, and table I think B1 has heating values and HFGs. Okay, so we'll be using table B1 and B3. All right, uh, B1, B3 of Stephen turns. Stephen turns. And from B1 we get for N-hexane, we have molecular weight of N-hexane, which is nothing but 86.177 kg per kilomole. We also have delta HC heating value, which is how much is it? 48696 48696 kilojoules per kg. And we have boiling point, but I think this boiling point is for 1 atmospheric pressure. We need to find the boiling point for 10 atmospheric pressure. That's where this Clausius-Clapeyron equation we are going to use. So boiling point is 69 degrees Celsius at 1 atmosphere. And HFG we have. HFG is N-hexane, 335 kilojoules per kg. Okay, all right. So now we need to find out the surface temperature or the boiling point of the droplet. I think everything. After that, we need to find out mu and CPG. CPG. So currently, what I'm trying to do is I'm going to take CPG as a gas phase N-hexane gas phase CP. Okay, and we will see its implications while finding the flame temperature. Okay, um, it will give you a good estimate in while finding the mass burning rate, but if you want to find flame temperature at that time, it will be way off. Okay, so CPG is from B3, so I have a value here. Let me just write it down. 330.4. Okay, let me write it down in mass. 3834 4 joules per kg Kelvin. Okay. All right, and also kg. It is also from the same table. Kg is 0.135. This is also for fuel. 25 watt per meter Kelvin. Okay, it's nothing but thermal conductivity of the gas phase fuel. The reason we need to select this is we are interested in mass burning rate, and the mass burning rate is going to depend on evaporation of the droplet. And which one is controlling evaporation of the droplet? The temperature difference from the flame to the surface and the gases present in between them, right? If the gases have higher thermal conductivity, then it is going to conduct a lot of heat. If it has less thermal conductivity, it is going to conduct less heat. If it conducts a lot of heat, the mass burning rate will be high. If it conducts less heat, mass burning rate would be less. So here, instead of selecting kg, if you select something else, let's say like kr, then it becomes a problem. It will not give you the correct mass burning rate. Okay. Mm, all right, that is one thing. And yeah, now we need to find out. Only thing left is we need to find out Ts. So Ts is nothing but T boiling. Ts is equal to T boiling at 10 atmosphere. So what do we use is we use Clausius-Clapeyron equation. Clausius-Clapeyron equation. So we all know what is Clausius-Clapeyron equation is. I don't need to say anything about it. So it's going to be ln of P2 by P1. These are all saturation properties is equal to hfg by r 1 divided by T1 minus 1 divided by T2. Right? Did I write it correctly? Yeah. So now we know what is the P1 here. P1 is 1 atmosphere, and we know T1. T1 is nothing but 69 degrees Celsius. So 69 could be converted into Kelvin. 69 plus 273.15, 342.5, 15 Kelvin. Okay, and HFG we know R is going to be 8314.5 divided by molecular weight of the fuel, which is 86.177, and that is going to be around 96.48, 96.48 joules per kg Kelvin. Okay, now let's substitute all the variables we know here. Ln of 10 by 1. So P2 is going to be 10 atmosphere, which is what we need to find for. Okay, which is equal to HFG 335 into 10 power 3 divided by 96.481, 1 divided by T1, which is 342.15, minus 1 divided by T2, which is what we need to find out, which is nothing but TS. All right. Now let's say if I rearrange this, let's see, 335 into 10 power 3 divided by 96.481 ln of 10 divided by this thing, and then 1 divided by 342.15. So T2 is coming out to be around 442.56 kelvins, which is equal to TS. Okay. There is probably a better way to calculate this also. It's better if you could go and find the real, instead of Clausius-Clapeyron equation, you can even check the tables for getting boiling temperatures or saturation temperature for 10 atmosphere. Okay, this is just estimating the, you know, boiling temperature for 10 atmosphere. The next one is nu. How do we find out nu? Stoichiometric coefficient. So we know it's N-hexane. N-hexane is nothing but C6H14. Okay, C6H14 plus it reacts with some A amounts of O2 plus 3.76 N2. It is going to react with air, and it is going to give us some, 6CO2 plus some some things we don't really need. Only thing is we need to know nu, which is nothing but A times molecular weight of air times 4.76, because 1 mole of air is 1 mole is nothing, it's 4.76 moles of air, right? And we have 1 into molecular weight of C6H14. So A we can find, which is nothing but x plus y by 4 for any hydrocarbon. So this is going to be 6 plus 14 by 4. Interesting. So you can do 2, 7, 7, 6, 2, so 12, 12 plus 7, 19 by 2. Okay. So let's say if you substitute here, 19 by 2 into 4.76 into molecular weight of air, let's say 28.9, and the molecular weight of is this is 86.177. Okay, this is how you find out stoichiometric coefficient, and it is going to be 15.165. 15.165. All right, this is new. So we found everything. We just need to find the B. So what is B? B is this whole thing. Copy it. Copy. Okay. So we know delta Hc, which we just found out. A 48696 kilojoules. 4869 divided by mu 15.165 plus 3834.4, I guess, right? And it's in kilojoules? No, it's in joules. And then T infinity is 1400 minus Ts. We just found out it's to be 442.56. 442.56 divided by QIL is 0, and we have 334 into 10 power 3. I hope that's it. Sorry, 335. Alright, let's see what is B coming out to be. 48696 into 10 power 3, 15.165 plus 4.4, 1400 minus 442.56 divided by 335 power 3. I'm getting around 20.544. So B is nothing but 20.544. Alright, so B is done. Then we can find M dot. So M dot F is what our interest is. F is 4 pi kg. Rs is nothing but radius to the surface. Basically, if you say fix the coordinate system to the center of the droplet, Rs is going to be the radius at which surface is present, and Rf is going to be radius at which the flame is present. Okay, and this is going to be divided by Cpg into ln of 1 plus d. Going to be 4 pi. Kg is we found out to be 0.135255. 0.135255. And Rs is, we have 200 micron meter, so this is going to be 100 micrometer. 100 into 10 power minus 6 divided by Cpg is how much was Cpg? 3834.4. 3834.4. Okay, and there is ln also. ln of 1 plus 20.54. Okay, this will give you the mass burning rate, and 1.54 into 100 into 10 power minus 6, 5, 3, 8, 3, 4, 1.36 into 10 power minus 7. 1.36 into 10 power minus 7 kgs per second. So this is the rate at which the mass is burning. The propellant, I mean the droplet is burning. Okay. All right. The first objective is over. What are the other objectives we have? The important objective is to find the length of the combustor. That is our next objective. So how do we find the length of the combustor? Second one is, I know the mass burning rate. I know the rate at which it burns. So if I could estimate the time at which it fully burns, that is going to be the, what do you call, mass burning rate. Sorry, that is going to be the droplet lifetime, right? The time at which it is going to end. And once we know that, we know the velocity, so we can easily find how much distance it has traveled before it is get fully, burnt, right? So that is what we are going to do. Length of combustor. So one of the assumptions in deriving all these function is the uh, uh, the droplet is in quiescent medium, which means gases are not moving, droplet is not moving, or in the sense droplet and gases are in state of rest, right, compared to each other. So relatively, so let's say here also you can apply this analysis. The reason is velocity of droplet and particles are same. So the droplet, if you sit on the droplet, you will see gases not moving, because it is also, since it is also moving with you, you both are moving at same speed. So you will just see gases are also gases at rest, and gases will see droplet is at rest, but you both are moving at some speed. Let's say if there is any difference in speed, let's say particle moves at lesser velocity than the gas velocity, then this whole analysis on which these equations are derived are the way in which these formulas are derived should be changed. So you cannot apply the same analysis when the droplets and the gases are moving at different speeds. But it is quite possible in real situations. We always encounter such um, you know situations where droplets and particles will be different. Okay, so one second. Hello, Francis. Am I audible? All right. I think Francis' mic is not working. Let me continue. So basically, what I am trying to say is the length of the combustor will depend on the velocity of droplets and also the velocity of gases. So if these two are not same, the whatever the formulas we use to derive it would be uh, different. Okay, so we need to take into account of convection effects. So when we add those effects, these burning rates will be different, and similarly the temperatures are also will be different. So to find the length of the combustor, first we need to find the droplet lifetime. So to find the droplet lifetime, again we already know the relation. It is going to be T, I think it is T naught or TD maybe. I don't know. what has been followed in the lecture. But so the droplet lifetime, it's going to be just the initial droplet diameter divided by evaporation constant K. Now we need to find this evaporation constant, but this evaporation constant is nothing but 8 times kg divided by rho L Cpg into ln of 1 plus B. So luckily we already found B, so we no need to repeat that calculations. What we will do is we will just multiply all the properties. So kg we found out to be 0.135. I think it's a little bit bigger than that. Yeah, 135255 divided by rho L 665, I guess. It's also given in the question. 664, okay. And CPG is 3834. 3834.4 times ln of 1 plus B is 20 point, how much did we found? 20.544. Alright, so let's say if I calculate this, how much is that coming out to be? 4 divided by 3834.4 divided by 21.544. Okay. The evaporation constant is around 1 point, right, 1.3048 into 10 power minus 6. So this is the evaporation constant we have. Basically, I think it will be in meter square per second. Okay. Now let's say if you substitute in the droplet lifetime, we have d naught, which is 200 micron meter. So 200 10 power minus 6 square divided by k, 1.3048 into 10 power minus 6. Okay, let me quickly multiply that also. 0.3048 divided by 10 power 6. So if you see, now we have the droplet lifetime to be 0.0306 seconds. So relatively speaking, you might say that this is very less, even less than a second. But how is this going to affect the length of the gas turbine combustor is something you need to understand. So now let's try to find out the length directly. So what is going to be the length? Length is going to be just the velocity of the droplet. Length in the sense, let's write it out. Distance traveled by the droplet. Distance travel, based on this distance travel, we are going to design that combustor should have this much length, right? So distance traveled is going to be, it's not called D, we'll call L. It is going to be TD times BD, and 0.0306, and velocity of droplet is also high, it is around 50 meters per second. So now when we multiply this, we get the length to be 1.5 meters by 3 meters. So ideally speaking, your whole gas turbine engine, let's say if you take, it might go maximum, you know, uh, 5 to 6 meters, right? So it might go more than that also, but the combustor will maximum be like 2 meters. So in that, if you so the we are talking about this secondary zone, right? So only the secondary zone, this big rogue, droplet came out and entered the secondary zone, and we are telling the secondary zone should also have 1.5 meters. Then it's going to be really difficult to have a very big combustor. So basically, you should not design in such a way that you will have this rogue droplet. You should make sure that nozzle sprays a very fine droplets, so that it can easily evaporate and completely combust before it reaches other parts of the gas turbine. Okay, so this completes the second part of the question. So the third and fourth, I just want to show it because these are the questions it's been asked in the you know assignments also. So we are not really in, once you find the length of combustor, it's basically fine for us. We are not really interested in flame, because at the end of the length of combustor anyway droplet is not going to be there. So this is just for the sake of completeness, we will just find the flame temperature. And there is some good reason to find the flame temperature, because we will see how off it is because of the calculation of Cp. Okay, so to find flame temperature, again we have a we derived it already. So let me write the equation here. It is going to be QIL plus HFG divided by CPG to 1 plus mu P minus 1 plus Ts. Okay, and similarly we are assuming that droplet is at T saturation, so this QIL will be 0. Now let's say if we substitute other values, HFG is 335 into 10 power 3 divided by CPG is 3834.4 into 1 plus mu 15.16, I guess 15.165, and mu is 15.165 into B is 20 point how much 544 minus 1 plus TS is, I believe it's 442, I guess 442.56. All right, so let's say if I quickly calculate this also, 15.165 20.544 minus 2335 into 10 power 3 3834.4, right? So I am getting it around 1678.43 plus 442.56. Okay, it is around 2120.98. Okay, we get flame temperatures is around 2121 Kelvin. Okay, but basically if you look at it, let's say if you run a n hexane uh, combustion at equilibrium, let's see, let's have a look at it. How much would it be the adiabatic flame temperature? So there is something called uh, the same table which I have been taking HFGs. So there is adiabatic flame temperature also. For n hexane, we have temperatures around 2273. Okay, so that's a equilibrium temperature. but in reality, 2121 is itself is a very high temperature for these things to happen. Basically, 2121 Kelvin, people basically never operate in that region. They have to keep temperatures to be less than 1800 Kelvin. So they try to either cool it down or they try to reduce it as much as possible by um, either performing lean combustion or by mixing. Okay, so that could be one of the reason it is coming very a little bit higher, the flame temperature. Anyway, so but if you get a good, probably this might be good approximate value for CPG. But if you have a more accurate or more guess, I mean more accurate guess for CPG, which is nothing but which is specific heat for the gas phase, then you would end up getting really close flame temperature. Let's say if you run a CFD simulation, and if you see what is the flame temperature you are seeing, and if you compare those two, you will get more accurate. So that is something I want to show you, and that is there. So the final question is, find the ratio of flame radius to droplet radius. Okay, let's see. Ratio of flame radius to droplet radius. We can write it like flame radius to droplet radius. So droplet radius, I'm just telling that radius at the surface. So basically it means that we have a droplet here, and we have flame over here, and what I'm doing is I'm fixing the coordinate at the center of the droplet. So the, what do you call, the radial coordinate is going to be, and this is going to be RS, and going to be RF. So this is what they are asking us to find out. For this also, I believe we have derived the relation, or at least we have discussed about the relation in the class. It is nothing but ln of 1 plus b divided by ln of mu plus 1 by mu. Alright. So then we have ln of 1 plus 20.544 divided by ln of, I guess it's 15.165 plus 1 by 15.165. So this is going to give us 15.165 second, and 21.544. So we have this to be around 48.07. So it's really far, very far. RF by RS is equal to 48.07. So which means the flame is like 48 times farther than the, you know, um, droplet surface. This is too much anyway. But these are all due to the average properties, as I said, the specific heat, the thermal conductivity, all those things will have effect. The reason is, why would the thermal conductivity be an effect? The reason is thermal conductivity of the gas phase is what we are discussing. So as I said, so here when the fuel comes and oxidizer comes, when it reacts over here, the lot of products are getting generated, and these products not only goes outside, it also goes inside, right? And because of that, this region filled here is not just fuel, it's fuels plus product. And just taking thermal conductivity of the fuel, Yeah, and if you try to estimate it, the fuel thermal conductivity might be lower than thermal conductivity of the products, right? Uh, and all these thermal conductivities are, we are talking about gaseous fuel and gaseous products. So let's say we know the, mass fractions and mole fractions of the fuel and products present in this region, and if we are able to correctly, uh, you know get a estimate of, very good estimate of K effective or K mixture in this region, then we will be able to get a very good estimate of how much this flame is present, and like what is the ratio of distance of flame to the droplet radius. Those, that will be more accurate, and the rate at which this is going to evaporate is also going to depend on Cp. That will also be more accurate if you have a good estimate. So um, and all these things are required only when you do this simplified analysis. If you are doing a detailed analysis, you can actually go with different species CPs, their thermal conductivities. You can solve the full Navier-Stokes equation, energy equation, species conservation equation, all these things together, and you will be able to get good results, and it will be more accurate results also. But the problem is it's computationally intensive, it's physically, complicated process. Mod like Modeling each and everything is going to be really difficult or really time consuming. Instead, people do this and get a good estimate, and they try to move forward with their analysis. All right, so that's it. This is what I want to discuss today. I hope this would be helpful for your assignment. So, Francis, you joined a little late. Maybe I will quickly recap what we did in the first question. So, in this question, what we have is we have a gas turbine combustor, and in a gas turbine combustor, we have fuel. Fuel is sprayed inside the combustor, and the fuel reacts with gases, and products are generated, and these gaseous products are expanded in the turbine. But what happened was there is one fuel droplet which didn't evaporate, so which we called it rogue fuel droplet. Okay, so this fuel droplet escaped this primary zone of combustor, uh, but after that it started little slowly. It is evaporating little slowly, and they are telling that the droplet and gas are traveling at the same velocities. Those things, and they also gave some uh, properties as operating conditions which is happening inside the combustor. Now our job is to find out, let's say if this droplet escaped, yeah, so if it is, I mean not if, it escaped, so we do not want this droplet to go out of the combustor. Okay, so we want to evaporate all the droplet which is present, I mean, which it has to be evaporated before it goes to the turbine. So if we want to do that, then what should be the length of the combustor I needed? So that is what we are trying to find out. So it is quite easy with this framework. The reason is we know what is the droplet lifetime, right? So what is the time it takes for the droplet to completely burn, right? That is the droplet lifetime. And if we multiply this droplet lifetime with the velocity of the droplet, then we can approximately tell that this should be the length of combustor. By the end of this combustor, the droplets will be fully evaporated, and uh, we will be sure that only gaseous uh, products will be entering the turbine. Okay, so the given data given data will be useful for you to evaluate these uh, this length of the combustor. So basically, to evaluate the length of combustor, we need droplet lifetime. So that is what we did. So initially we started with mass burning rate. So it's just to show how to calculate mass burning rate. So we can so this is the relation. It's already derived in the class, and um, kg rs kg, it's a thermal conductivity of the gas phase. Cpg is the specific heat of the gas phase, and b is some factor which we need to find out. uh, so that is also given here. So basically we took these values hc, cpg, hfg, all these things from the tables from SR turn. And then uh, one more additional thing is they have given that pressure is at 10 atmosphere, but this and we also don't know what is the TS. That is one of the problem. TS is the surface temperature of the droplet, so it's nothing but the droplet's surface temperature. So if we want to know droplet surface temperature, basically droplet is at saturation temperature and droplet is evaporating, right? So it should be at saturation temperature, and whatever energy comes into the surface of the droplet, it's going to use it for evaporating. So there's going to be energy transfer based on, like, it's just hfg energy consumption is going to happen. For that, it requires surface temperature should be at saturation temperature, but that saturation temperature should be at 10 atmosphere. It shouldn't be at 1 atmosphere. So what we did was we used Clausius-Clapeyron equation in order to get the saturation temperature at higher pressure. So for one pressure we know HFG and the boiling temperature of the uh, NXN, which we got from the tables, and we use this equation to get the uh, boiling temperature at 10 atmosphere, and that is going to be the temperature of the droplet. That is why we name it as TS. And another thing we need to know is stoichiometric coefficient, and which we know it's a mass of oxidizer by mass of the pure at stoichiometric condition. And once we find out this, we can find B, and once we find B, we can find m dot. And similarly, you can find the droplet time. For droplet lifetime, you require the evaporation constant, and evaporation constant also we have a relation. Evaporation constant you can find, once you find evaporation constant, you can find droplet lifetime. Droplet lifetime if you find, then you can find the length of the combustor. This is the combustor length I require. Okay. And later we also calculated flame temperature, whose relation is also given in the lecture, and we just merely substituted all the values which we already found for finding other questions, um, and we got flame temperature and the ratios of what do you call flame radius to droplet radius ratio. Okay, so that is what we did. So do you have any
So,
questions, Francis? Yes.
I have some doubts on the property relation. I mean, on the pure substance. Can I ask?
Sure. It's is it related to the um, this question, or it's related to the
No, it's not actually related to this one. It's actually if you will be lectures back.
okay, okay, sure, sure. Yeah. Then
So actually, if we draw a PET diagram of the substance, I mean there is a triple point and critical point diagrams in it. Like that's the sublimation curve and vaporization and those three curves,
right,
PP diagram of the pure substance.
right.
So where will we locate the both? I mean temperature and vapor mixture region. Is the there is a dome for the PT. If we draw that TV diagram, we will be having a dome, and inside the dome we are having both the vapor and liquids in it. So can we locate that mixture region in that PT diagram anywhere?
I see. So in the PT diagram, we have this. Let me see if I have it in notes.
That triple point diagram of the substance which expands on
Is
uh,
this kind of diagram? Is that what you're talking?
something like that one. But there is a one more sublimation line at, which
Uh-huh.
connects the chip. Some,
This is the
yes, sir.
diagram, right?
Yes, sir. So
So, mhm, yes,
here can we locate the dome? I mean the mixture region.
mixture region. Okay. So you were telling this region, is it? This dome.
Yes, sir. Yes, sir.
You want to locate it here.
Yes.
Okay. Let's see. So these are all constant temperature lines. Okay. And you are trying to do it here. So inside the dome, what happens? It's going to be uh, temperature is going to remain same, right? Which means it's a single line.
Okay, sir. So we can locate it. It will be constant lines,
Right.
isothermal line.
It will be a constant line because these are same temperatures, right? So let's see. So what are these are constant temperature lines, and let's say if you select one temperature and if you increase the pressure, let's say, okay. So let's say you select this line, and what do I do is I'm in the liquid side, and the pressure keeps on decreasing as I go to the gas side, right, for the same temperature. So let's say from here to here, if I'm going, huh? So the pressure is also remaining constant, right?
Yes, sir. In the phase change region, we will the pressure will be on.
Only volume expansion takes place, right? In the phase change region, this is the mixture region, right? So both pressure and temperature remains constant in this during this dome. So that is the reason you should represent this with one point, which is Psat and Tsat, and that is what is lying in this line.
Okay, sir. So it will be the line here.
Right, right. So line in the sense, let's say if you select a temperature, okay, let's say this is the temperature. For volume, there will be during phase change, there is a volume change, so volume will increase, okay, but the pressure and temperature is remaining constant. So in a PT curve, it's just a point for that temperature. So now you are increasing the temperature. So what happens? The pressure also increases. So it draws a line, and all these happens at this curve, fusion curve. Let's say, okay, this is liquid vapor. This one, this curve. All these happens at here. Okay, so uh, there is actually one. So let's say if for this line, I mean, ignore this. Only the the mixture, what do you call, gas, uh, I mean liquid vapor mixture region is there, right, inside the dome. Inside the dome, the P and T are not varying. For a given T, P is not varying, which means that corresponds to this curve where for a given P, for a given T, P will not vary. So it's actually one single point. This line is actually one point here. Similarly, you can draw other lines which will correspond to another point, and then you will add all these things to get this line. Does that make sense?
Yes, sir. So if we in the same curve, if we are saying about a T saturated line, if we take a certain pressure, about 550 megapascal, then the T saturated will be, if you draw the straight line from that horizontal to that temperature, and the line which intersected at the curve will be the vapor line. Vapor line will be the T saturated.
This one you are telling, right?
Yes, sir. If
Yeah.
you are,
So,
oh,
so for a pressure, let's say you want, you just draw that straight line over here. Okay, and for which temperature, right? So for any pressure, if you draw this line, it will intersect at this point, right? And the corresponding temperature is going to be your Tsat. Is that what you're
So
asking?
the temperature correspond to that fusion line, and if we intersect the those cannot be desaturated, isn't it?
Which one?
Fusion curve.
Can you repeat? This is, let's
I
say, if you
mean,
take this line.
yes, sir. If I that it also intersected the fusion curve, isn't it? So
Right, right.
I is that temperature some kind of desaturated or anything, or
See, this is T saturation, but for solid liquid conversion. This is T saturation for liquid vapor conversion.
okay, sir.
Okay, so there are two T sats. I agree, but there are also two different phase changes happening, right? So for solid liquid, this will be, for liquid vapor, this would be. Basically, I'm not sure.
So
This will
when
intersect
we
something like this.
okay.
So probably the other curve would be something like this. Okay, for most of the materials. So I may need to look into what the curve would really look like. You may not be end up having such situations. You might have in this place, like if you want to convert solid to vapor and the liquid to vapor. So this kind of situation you might have, but I'm not sure you will have this kind of situation. Will you have? But anyway, these are two different saturation temperatures. That is true.
So actually, this graph is actually similar to the graph of that water. I mean
Ha
the
ha ha. So
which
only for water you will have this increase, I guess. Is it? Something was different with water other than, okay, anyway. So let's say if you take 1 atmospheric pressure, okay, and then you draw a line. So at 1 atmospheric pressure, the 273.15 Kelvin is the freezing point, right? And 100 degrees Celsius is the boiling point. And these two lines are actually corresponding to that. Okay, this is T freezing and this is T boiling. Both are saturation, but it is dealing with two different phase changes, different phase changing phenomena. Does that?
so but when we are looking for that steam table, we will be only having one P saturated, isn't it, corresponding to one pressure.
So in steam tables, it's always about liquid vapor conversion.
Okay, sir.
So it will always, it focuses only on this. It focuses only on this part of the curve.
So is there any other table like which for these other T saturated, like for the sublimation and for fusion curve?
Right. Good question. Actually, I haven't came across such tables. Uh, it is also, where will you actually use this? So practical usage is less, I guess, for this, or maybe someone who's interested in solid, liquid, evaporation, phase change things, they might be interested. Um, but those people also, they don't really use. So the tables come only when you are having engineering applications, right? Like in steam tables, we use it in steam turbines, in industries everywhere. So that's why they introduce steam tables. But in fact, in, let's say, in research, when people do research, they don't use steam tables. They use some sophisticated methods. They use some sophisticated, equations. Uh, you know, the yeah. So it will be depending on, there are different saturation models. So those saturation models will give you T saturation for solid liquid conversion, solid vapor conversion and all. But I think you may not be able to find tables exactly. So there might be models which will be like, let's say my T sat is nothing but some constant times pressure plus e power something log of something, all these things it might depend on. Okay. Or if I want to find HFG, right, HFG in the sense SF, solid to fluid conversion, right. Other time it might depend on some pressure, saturation temperature, right. So there will be different models which will be sometimes exponential dependence with pressure and temperature, sometimes uh, the quadratic dependence with pressure and temperature, sometimes combination of these is power loss. So all kind of saturation models are present for modeling this solid liquid or solid vapor. Even for liquid vapor there are saturation models, but engineering applications are not really interested in these models. They just want values. That's why we have steam tables. That's why in engineering we start with steam tables. So that's why you may not be able to find solid liquid tables, but I'm not really sure.
Okay, so if you are analyzing any this kind of tables in the ANSYS, I mean fluent, ANSYS fluent or anything, they will be actually using this kind of table behind it. I mean, do we need to depend on such software, or do actually in the research uh, area they are actually coding it themselves?
So basically, what happens is in ANSYS also it doesn't automatically take care. We have to give everything separately. If it then only your model is complete. So it might run something and it might give you some results, but it might not give you the proper results, or maybe it might give you incorrect results and you may not know. So in ANSYS also they will give proper models, saturation models, and I mean whoever uses it, they should know that I need a saturation model to use, and they should also give it properly to the ANSYS. And there should be some way in ANSYS. I'm not really sure about ANSYS. Uh, but by default, ANSYS will select some model. It might even select that saturation temperature is same, HFG is same, and all these things it might select. I mean, constant saturation models, all those things it might select, and it might do something for that. But in research, what usually people do is they take care of it. Let's say if you don't use ANSYS, if you use some other software, some other uh, you know let's say if you take COMSOL, that is also an commercial software, and there is an open source software, OpenFOAM, which is for CFD. There we make separate saturation models, and it should be taken care by the user. So it has nothing to do with the software. The software can, whatever you give input, it can give you the output. That's it. So if you give proper inputs, it will give you the output, whether it would be ANSYS or OpenFOAM. So we should be knowing whether we need to give which saturation model in order to run any simulation. Does that answer your question, Francis?
Yes, sir. So, and another thing is actually in this diagram, the in the intersection of these 3 points are actually critical point, and for the vapor curve, there is a critical point, isn't it? One is triple point and another one is critical point. So there is a statement like if at the after the critical point, the distinction of the vapor and liquid is non distinct. That I mean, the distinction with the liquid and vapor is non-existent. Can I explain that point? I mean, after the critical point, the distinction with the liquid and vapor is non-existent.
Right, right, right. So basically, this is where the critical point is, right? So in the PV graph, if you look at it here, um, so let's say if you keep on increasing temperature to a critical temperature, um, I'm not sure what is that temperature. For water, how much is the critical temperature?
So three, I think it is 373. degree Celsius.
at 1 atmosphere.
22 megapascal.
22 megapascal and 373.
Critical point.
So, after what happens, uh, basically, it's a very, how do I say, it's even I feel that um, even I don't know what it really means. The reason is
What my doubt is actually I can understand whether it will be liquid or gas.
ha
I
ha ha
mean, above that point, it is written like we can't compress the vapor to liquid form since there is no phase change. So is it like if the substance is in liquid form, then it cannot be converted to the other form, or if it is in the gaseous form, it cannot be converted to liquid form. Cannot understand what there actually it
right,
is.
right. So it is it's not like that. So it's actually liquid is there, and if you raise its temperature and pressure to that level, it doesn't require any additional energy to get converted into gas. It can automatically get converted to gas. So there is some
So there is no
enthalpy.
latent heat.
There is no HFG for the gas, right? The
Yes, sir.
HFG goes to 0. So without any energy, I can convert this liquid to gas. Or there is also, it's called supercritical, state of matter. So I mean state of liquid or gas. It's called supercritical state. It's not liquid state or gas state. It's called supercritical state.
Yes, sir.
Above critical is called supercritical state, right? So there, even the equations of state is also different. It's not liquid, it's not gas, right? You cannot give an ideal gas equation of state. You cannot. So basically, how whatever we know, how the gas behaves here and how the liquid behaves here, all breaks down here. Okay, so you cannot use ideal gas relation here. You cannot use the tell that row of liquid is same or row of liquid is almost you know same, right? That you cannot say that. So the separate equation of state comes into picture. So it's a different state of matter. So uh, it's
So,
little
but
difficult to
how we
understand.
distinct? I mean, can we write any, draw any line like this? This after this till this line is liquid and till this line is gas. I mean, it's actually at the top of the dome. We don't know actually the contour. We can't separate it using any contour. Is it like that? I mean, sir, you have written liquid and gas at the left and right, isn't it? So, till which point we can write that liquid, and to which point? I mean, if we are drawing a horizontal line, then
Okay, so that is, so you are telling like this is liquid, this is gas, or from where this thing starts, you are asking,
yes, sir, yes, sir,
right,
yes,
right. So as you go above and above this dome, na, so it becomes as I said, it reaches closer to the critical state. So at this point you cannot really draw a line like this and say that this is the place liquid it will be, and then suddenly it goes to supercritical stage. So you cannot really draw a line. It's like, how do I say, it's like a smooth transition from this liquid state to a supercritical state. So it might happen somewhere like this. Let's say here you might see that it is well behaved as a liquid. The behavior will keep on slowing down, and then suddenly it becomes a supercritical over here. So we cannot really draw a line, uh, or maybe I don't know. Actually, I am not an expert in supercritical, you know, uh, states matter. I don't really deal with that much high level of complexity. So, but you can ask this kind of questions to some researchers who work in supercritical uh, states of matter. For example, let's say if you take a rocket engine, okay, liquid rocket engine, there will be evaporations, combustion, and all happening, and all these rocket engines operates at, let's say, 10 megapascal, 20 megapascal, even 50 megapascal. and 50 megapascal and at a very high temperature, and all these things happen inside. Whatever we do is we will directly apply ideal gas and we will try to solve it. But really what happens is the supercritical combustion happens inside the engines. Even the solid propellant engines are in the basically importantly the liquid propellant engines, there will be supercritical combustion. So if you talk to some people who are really working in this supercritical combustion, then they might be able to give you a more better answer than me. But what I feel is, I feel that there won't, I don't think so you can draw a clear line and tell that after this point magically liquid becomes supercritical state. In reality I don't feel that would happen. Does that answer your
Okay, sir.
question?
Yes, sir. So one more thing, so actually, is quality a property?
Which one?
Quality. There is a we can call X isn't it?
X,
The ratio.
right, right. The ratio of amount of fuel, sorry, fluid, right? How do you say liquid present in the, ratio of amount of gas present in the mixture, right?
Yes, sir. Is it actually a quality? A quality? I mean property.
So, so what are the things you call property? So density you call property, right? Uh, Specific volume you call property. This is just a fraction, right? So how much amount of specific volume is this? How much amount of specific volume is that? So see, property has to be something. Let's say if you say that it will fix your system coordinates, right? So let's say if I have VF and let's say if I have XF, then it will, maybe you can say quality as a property. What do you think? So property has to be something which should fix the coordinates of the system, right? So let's say if you
Yes,
specify
sir.
P and T, P and T are properties. If you specify P and T, it will, based on the equation of state, it will fix all the coordinates of the system and it will tell everything about the system. I mean, it will determine the system, right? Similarly, for a phase change, you know, uh, system, you will have P, you will have VF, VG. So these three things is required to fix a system. Either you can have P, VG and VF, or you can have P, VG and XF. Similarly, you can have P, VF and XF. These things can also fix the system because XF is going to tell me how much amount of fluid is going to be present, and the remaining is going to be gas. So automatically everything gets fixed. So probably I feel quality should be a property.
Okay, sir. So if it is a property, then will it be a extensive property or intensive property? I mean, it's actually depend on the mass of the matter, isn't it? So can you say it an extensive or
So how do
intensive?
you define quality?
Quality is actually the mass of vapor by mass of liquid plus mass of vapor.
So XF is nothing but mass of vapor by mass of liquid plus mass of vapor, right? So maybe if I do it like
So,
GG, right? So now let's say if I do this, then 1.
it's actually dimensionless, I think, since both are mass.
Yeah, but then it should be an intensive property, right? So is it going to depend on, let's say I have 40% vapor and for 60% liquid. So I didn't say anything about the mass of the whole system, right?
Yes, sir.
So it actually doesn't depend on extent of the system. Question, let me think. So basically, when you say intensive property, the let me see, intensive property is nothing but extent volume of the system is divided. So basically, all the specific quantities are intensive, and all the non-specific quantities are extensive, right? So okay, I didn't take. Extensive. Basically, if it contains the information of the extent, let's say if you take a specific volume, uh, by the way, if uh, do you really say quality to be V? Shouldn't it be specific volume in terms of?
Uh, Actually, I think it was based on the mass. I don't know specific volume.
Okay, so mass, how do you write mass of the gas and mass of fuel and sorry, fuel, not fuel, mass of vapor and mass of liquid? How do you find it?
I think actually the that was actually given in the question, like it will be the mass of vapor will be actually given usually.
I see. So, uh, let's see, let me quickly pull out some books if possible. Mhm. Quality. What do you think? Should it be intensive or extensive?
So I think it will be since the quality will be changing according to the mass of gases in it. So I was confused. It can be extensive. I mean, if we move to the one side of the curve, I mean down, the mass of gas is actually increasing. So actually, according to that, mass is changing, isn't it? So can it be in extensive?
The dome is based on pressure and specific volume. Both are intensive, right?
Yes, sir.
Uh, now, how do we? So you, I mean, I'm telling that it may not be right to tell that based on that it might be extensive. If it is true that it is mass fraction, mass of you know uh, liquid and vapor, so mass is an extensive quantity. So I would probably expect uh, quality also should be an extensive quantity, right? Okay, let's see. basically what Google says about it. Okay, intensive property and an intensive property. It is mass fraction. Since mass is coming, that's what is creating problem, right? Whether it is an extensive or intensive. Maybe you can think like this also. Let's see. Uh, Say you have a this is a basic test we do, right? So let's say you have a container and you have a 40% liquid and for 60% gas. This is 1 meter cube. Okay. Now let's say if I divide this into two, I would have two containers with zero point 0.5 meter cubes. So while dividing, what happened? The 1 meter cube become zero point 0.5 meter cube. So V is nothing but an extensive property because it depends on the extent how big uh, you know the system is. That is clear. Now how much liquid and how much gas would be present here? What do you think? So initially I had 40% liquid and 60% gas, and the XF is going to be simply uh, zero point 0.6 XF or XG, let's say XG, zero point 0.6 by 1, which is nothing but 0.6, right? Now how much would be L and G, how much would be XG? So when we defined the system, we defined it as 40% and 60%, right? So which means 40% liquid is present, uniformly distributed, 60% gas is uniformly distributed. Until you have that assumption, when you divide it, again you will expect the same 40% liquid here, right? And 60% gas here. But only thing is amount is different. Exact mass amount is different. Similarly, as I said, Xg is nothing but mg by mf plus mg. That is true. But you reduced mg by half, mf by half, and mg by half. So all these half gets cancelled, and you end up getting same xg's. You understand? The mass fractions are the, that's why it's called mass fractions. Compared to relatively to the other mass, how much you are, you know, higher or lower. That is the mass fraction. So so again you will get xg to be 0.6 only, which makes this as an intensive property. You can even, instead of 40%, you can even tell that 4 kg of liquid and 6 kg of gas, total 10 kgs. Okay. Now you divide by half, you will have 5 kg, 5 kg. How many kgs of liquid and gas you will have? 2 kg of liquid and 3 kg of gas. Similarly, 2 kg of liquid and 3 kg of gas. So masses are different, right? But let's say if you calculate xg for the 1, you will have 6 by 4 plus 6, and for 2 you will have 3 by 2 plus 3. 6 by 10 is 0.6. 3 by 5 is also zero point 0.6. So I get same xg's, right? This doesn't depend on extent of the system.
So actually, how did you change that four and six and two and three? I mean, uh, we are having how this four and six came.
So I just randomly took some number, any number you give.
So actually, if we are taking the first box, I mean the 2 kg and 3 kg, if we are at this state we are getting zero point 0.6, and if we heat it, then the amount of vapor will be increasing. So then it could be 4 or 5. Then if we again take the quality, then it will be actually 5 by 2 plus 3, isn't it? So according to the vapor content, the X is actually changing, isn't it?
See, you are talking, so whether it is a, so um, let's say you have a, while heating, okay, XF is changing, I agree, but pressure is also changing, right?
Actually, the pressure will be we can make keep the pressure constant, isn't it? Like there was an example for that drawing that we will be taking a
No, no,
uh,
you keep it the, fixed container. We will talk about fixed containers, okay? So I agree with, you can have a piston and you can have the pressure. So during heating, there are a lot of places the intensive variables change. So we are talking whether this XF is a intensive or extensive, right? So when you are talking like that, you should compare. You should just think. You should not think about process, whether it goes through a process or not. So during a process, lot of intensive variables vary. So let's say when you have a adiabatic heating, the temperature varies. The when you have a adiabatic work output of the system, or isentropic, what do you call, what is that called, isentropic expansion, the temperature and pressures are varying, right? The same thing, but temperature and pressure are intensive properties. We shouldn't think about whether the during the process what happens to the intensive properties. During the process, intensive properties should vary, right? The Where to find whether it is an intensive property or not, you should uh, think whether if I have this system and if I break it down, or if I add another system, will the uh, you know property vary or not. That is the thing. So let's say mass is a property. I have 10 kg mass. Now if I divide it, I have the system becomes 5 kg 5 kg. That is the difference. But the 10 kg mass is at 1 atmospheric pressure. Now if I divide it, both the system is going to have 1 atmospheric pressure only. It's not going to have zero point 0.5 atmospheric pressure, zero point 0.5 atmospheric pressure. There's a difference between mass and pressure, right? Mass is an extensive property because it depends on extent of the system. What is the amount of what do you call, the matter present in the system. And but pressure doesn't depend on that. It still says 1 atmosphere. Same with the quality also. Initially, if you have this much quality, if you divide the system, the quality will be remaining same only. If you heat it, properties vary, right? Intensive properties also vary. So is that clear, what I'm trying to say?
Yes, sir.
So
Yes.
you understood, right? So during a process, lot of properties vary. So you can keep the P to be same. Similarly, So it is true that you can put it in a piston, cylinder arrangement, and you can keep P to be same, but it doesn't mean that the intensive property will not vary always, right? In some other processes, properties keep on varying, right? So that's why uh, processes is expected. So even let's say in any cycle, you draw a PT curve, right? Their properties P and T varies throughout the cycle. So that you shouldn't compare. You should just compare whether the pressure at that point, does it depend on, let's say if I have 1 kg system, this is my pressure. If I have 5 kg system, will it be different or will it be same? That is the thing it should depend on. It's not really the process.
Okay, sir. I understood.
All right.
Yes, sir. So one more thing, the entropy is actually intensity property.
Entropy, yeah, entropy is an intensity property.
Okay, sir.
There are two entropies. There are like uh, there is also, like we have enthalpy. There is capital H. There are small h, right? Specific enthalpy. Similarly, there is specific entropy. Specific entropy is an intensive property. Entropy is nothing but mass times specific entropy, which is an extensive property.
Okay, sir. Thank you, sir.
All right.
Yes.
If there are no more questions, we will meet for one last time in the next class. Okay. Around, I think it's on 21. So we will just discuss all the topics which have been covered in this course. And if you have any questions, you can come back again and ask me in the next class. Okay.
Okay, sir. Thank you, sir.
Thanks, Francis. Bye.